Let's start today's lecture. Today, I will talk about the triple helix, quadruplex, I-motif structure of DNA and RNA. This structure is one of the local conformation of nucleic acid. And especially this structure has an important biological function. But maybe you don't know about the chemical structure of this structure. To understand the function of this structure in living cell, we have to study about the detailed information about this local conformation. This is the structure in double-strand DNA. You know that guanine binds to cytosine and adenine binds to thymine by hydrogen bonding. It means that hydrogen bonds are key for DNA structures. And especially in the case of such a hydrogen bonding, most important is that the lone pair. Especially in the case of guanine and cytosine, lone pair of oxygen bind to the hydrogen is Na2. And the other hydrogen bonding consists of the same manner. In the case of adenine and thymine, hydrogen bonding makes such a binding. It means that such a lone pair and hydrogen is very important to form the DNA structure. You know that such a structure is called as Watson-Crick type. But not only that Watson-Crick type, but the Hughes base pair is in the double-strand DNA local conformation and the low RNA structure. In the case of guanine, you know that guanine binds to cytosine, but guanine can bind to guanine. Usually, this side in guanine binds to the cytosine, but not only this side, but this side binds to the other base, because N and O oxygen atom has a lone pair. It means that this atom can bind to the hydrogen by hydrogen bonding. It means that the guanine can bind to the guanine. And in the case of adenine and thymine, usually this site of adenine binds to the thymine. But you know that the lone pair in this N atom and the hydrogen can bind to the thymine because the thymine has a lone pair at this side and the thymine has a hydrogen on this side. This hydrogen bonding is called as Hughes base pair. This Hughes base pair manner is very important to form the DNA local conformation. So at first, I want to explain about the triple helix. This is a model of the triple helix. White strand means double-strand DNA, and the yellow line is a triple helix. Double-strand DNA has a major group and a minor group. In the case of triple helix, the third strand binds to the double-strand DNA in the major group. Okay, so can you understand why third helix can bind to the major group in double-strand DNA? This is the structure of the base pair, guanine, cytosine, and adenine, thymine. And this side is the major group, and this side is the minor group. Okay, in the case of this one, This site is a major group and this site is minor group. And in the case of guanine and cytosine, new guanine can bind to the major group site in the guanine and cytosine because this lone pair of N atom and O atom bind to the hydrogen to the other guanine. It means that this third strand can bind to the double strand DNA. In this, by the almost same manner, thymine bind to adenine as the major group in double strand DNA. This is the manner how to make the triple helix in the double strand DNA plus single strand DNA. Where does this triple helix formed in the nucleosome? This is the XX chromosome. So you know that in the case of XX chromosome, one side is inactive and the other side is active. So how to select the active side and select inactive side? From the side, RNA is transcribed, and this RNA expands to the other strand. And actually, this exist RNA bind to the double strand DNA. And this site is inactive, and this site is active. Okay, this is inactive, and the RNA binding site is inactive. So at this inactive chromosome, RNA binds to the double strand DNA. At this case, RNA and DNA might be formed the triple helix. What is a quadruplex? Quadruplex, it forms guanine-rich strand, single-strand DNA, and in this structure, guanine binds to the guanine by Hughes-Stein style. Okay, and especially in the case of G quadruplex, guanine binds to the guanine each other, and 4 guanine forms one Z tetrad plane, and in the case of the promoter of the oncogene c-MYC, this lot of G-rich strand forms the G quadruplex by the Hughes-Stein base pairing, and stacking each G tetrad plane. Okay, in this structure, most important is that the lone pair and the hydrogen. This atom makes the hydrogen bonding, and hydrogen this Hughes-Stein base pair by the hydrogen bonding is very important for the G quadruplex forming. So where is the G quadruplex in the nucleosome? One example is the telomere region. Telomere region is the terminal of chromatin, and this region is very important for the cell lifetime on the cancer. And the other side, the promoter has a lot of G quadruplex forming sequence, and this sequence is very important to control the transcription. This is the structure of telomere DNA, and the almost same structure. This is the G tetrad plane that consists of the 4 G guanine bases, and this G quadruplex structure consists of the G tetrad plane, 3 G tetrad plane, and each tetrad plane stacked each other. This is a mechanism how to make the G quadruplex from the single strand DNA. This sequence is a telomere DNA. Telomere DNA sequence is TTAGGG repeat. And especially guanine can make this hydrogen bonding each other. And it becomes such a happy loop strand. And then there's a single strand bind to here, and other strand bind to here, makes such a digital plex step by step. Digital plex is very important for controlling the telomere length. This is the relationship between the telomere length and cancer cells. In the case of normal cell, telomere length is shorted, and it results in apoptosis. But in the case of cancer cells, telomerase can elongate the length of telomere terminal, and it means that this cell it becomes cancer cells, because these cells cannot die by apoptosis. And especially telomere lesion can make the digital plex. And if we add the digital plex binding molecule to stabilize the digital plex, telomerase cannot bind to this DNA, and it means that the telomerase cannot work as a telomere lesion and cannot elongate the length of telomere. It means that this such a digital plex and the digital plex binding molecule to stabilize the digital plex is very important, and can prevent the telomerase and might suppress the cancellation. On the other hand, not only the telomere, but the promoter has a digital plex. Digital plex binding protein bind to digital plex, and if this protein can stabilize this structure, this structure inhibits the transcription from this site. It means that the digital plex is very important to control the transcription. And last one is the eye motif. Eye motif is formed at the C-rich region. This is a structure of base pairing of the CC site. And the cytosine can bind to the cytosine by hydrogen bonding. And especially this H is very important to form the eye motif, because if there is not this H, C can form the hydrogen bonding to the other C site. But in the acidic site, such a H bind to the lone pair of N atom, and it results in the hydrogen bonding, 3 hydrogen bonding each between the C and C. It means that this hydrogen bonding contributes to the stabilization of eye motif structure. It means that this structure is a cartoon of the eye motif structure. This yellow site is a cytosine. Cytosine binding. Like a digital plex, but the actual digital plex is formed at the G-rich structure. But the eye motif structure, in the case of eye motif structure, This structure is formed as a series structure. This is the topology of the iMochi structure. Most important is that the CC base pairing is very important, and the iMochi has 4 strands in one iMochi structure. And I already said that the iMochi structure formed at not neutral pH, but depend on the order, the environment condition. And the acidic condition is best for iMochi to form such a structure in the solution. But in the case of neutral pH, it's no problem to form the iMochi, but it depends on the sequence. This is an example of the sequence to form the iMochi. Especially this name means promoter, especially CMIC and C-kit, CMIC, and CMIC means oncogene promoter. Oncogene promoter has iMochi forming structure. You know that the G-rich DNA strand forms iMochi. It means that the complementary sequence is Z-rich sequence. And you know that the Z-rich sequence can form the G-duplex. It means that in the several DNA sequence, other side form the G-duplex, and the other side can form the iMochi structure. It's very interesting point. This is an example to form the G-duplex and the iMochi. Both structure is very important for the function on the DNA. For example, it is for the controlling transcription and replication and so on. And this section, I didn't explain about the detailed information, but next lecture, I'll introduce about the detailed information about the G-duplex and iMochi.